you've just seen how an OFDM system works, and you've also seen how it can be quite useful in situations where you've got a frequency selective channel, like with a multipath and mobility system. And in this last section, I will try to show you a slightly different, but with similar characteristics scenario, in this case, interference and narrowband interference. And so at the end, we'll see a practical demonstration with over-the-air and real hardware, real radios, with a comparison between an OFDM channel, an OFDM system, and a single carrier system in the face of said narrowband interference. But first, and maybe as a way to kind of have a break from all the implementation details and all the theory behind the channels and the multipath, we'll try to look for a example of a narrowband interfering system, and I will take the opportunity to show you some different elements as how you can look at the spectrum using the radio, some kind of spectrum monitoring, and a few parameters, a few elements that to look for and to keep in mind when you are playing with and looking at the spectrum. So for that, I've got a quite simple flow graph with a recipe source, which will be what gives us the samples we want to study, and a whole selection of 4 different types of GUI blocks that will show us different elements of the system, and we will try to compare and see what uses they have and what difference they have. And in this flow graph, we will play with mostly 3 different parameters. The first and the most simple one is the center frequency, so we will focus on the ISM 2.4 GHz band. And so I've set up the center frequency GUI range accordingly between 2.4 and 2.5 GHz. And we'll play also with the gain of the reception chain. And finally, something that usually you don't really change at runtime, and in this case we'll do it, and I'll discuss a bit what the impact of that. We will also change a bit the sample rate. So if I launch this flow graph, you can see that at first the parameters are just described here. So we are 2.435 megahertz of center frequency with 1 megahertz of bandwidth and 50 dB of RX gain. And we've got 3 tabs that we will explore one after the other. And in the first one, so we've got the 2 main basic sync types. So we've got the time sync, which is basically an oscilloscope. In this case, we can see that there's not that much, but sometimes we've got bursts. There appears to be something going on this band, on the spectrum. And on the frequency, on the bottom plot, the frequency, the FFT plot, we can also see that we have sometimes some bursts, but we don't really have any information on which band they use, when they appear, when they arrive. If it was a continuous transmission that we could actually see, we could be fairly simple to understand what's the bandwidth, what the frequency, the center frequency of this transmission would be. But in this case, since it's bursty, it's really hard to get the feel for what's going on. We could get more information, which we had if we put it some max roll, for example. We could get a feel for what's the highest system. But we won't do that here. Here we will try to actually use a third type of plot, which is way more simple to understand in this case, which is the waterfall plot. And what it is, it's basically a combination of time and frequency plotting. So we've got each line in the frequency axis, which is the result of one FFT. So same thing as what we would get in this plot. But here, instead of gain axis, it's in the colors. So red or even white is the highest power, and blue is the lowest. And each line goes one after the other in time, so we can actually get a feel for how long a transmission lasts, and if it changes frequency with time, for instance, and things like that. So it's really useful as a tool to understand what's going on in the spectrum, especially with bursty transmissions. Now, for instance, if we want to see more signals, we could say, okay, maybe we are missing some signals, or maybe we are going to increase the gain. That could be a way. But here, since this plot is set up the way it is, when we increase the reception gain, we also increase the noise level. And so we don't really increase the contrast of what we're actually seeing in this plot. And that's because the scaling, the way the colors are matched to a specific power value did not change there. And there would be a way to change that. If we middle click, we could get into some parameters, and there's the int min and int max value. So we could maybe some -100 for the minimum level, saying that -100 dB is the minimum level that we want to affect to our color scale. It's not really practical and really easy to use. And for that, I would advise you to use the forced block. So previously we were using the waterfall sync block, and I would advise you to use the category thing, the basic one, which is basically a combination of most of the basic plots. We've got the time domain display as before, we've got the frequency display and the waterfall display, also a constellation. We won't be using this one. For the time domain and the frequency domain display, they work well, but it has a slightly less features. For instance, it's hard to put on triggers in the time domain display. So if you want time and frequency displays, I would advise you to use the dedicated things. But for the waterfall display, it's actually has almost more features, and the main one is in the form of this auto scale button and the two sliders here that allows you to change the limit of the color scale, which is way simpler to use. So you can see you can change that in the dB scale. You can even change the type of coloring scheme you want. The color one is a good choice. You can also change the FFT size at runtime. That's quite useful if you want a bit more detail. Of course, you need to change the scale every time also. That's fairly simple to do. So yeah, for instance, here we can see that there is actually quite a lot of stuff going on this channel, but yeah, it seems to span the whole bandwidth, and so it's hard to know when it starts, when it stops, everything. And that's where, for instance, the sample rate could come in from, because right now we are at 1 megasamples per second, and we are looking at 1 megahertz of bandwidth. So since we are using complex samples at the radio hardware, we basically have a one-to-one relationships between the sample rate and the bandwidth we can actually look at the way we sample it. And so if we want to increase the bandwidth we look at, the only way really is to increase the sample rate. So for instance, if I put 20 megasamples per second here, we can see that now we get a bit more information, and we can see that we can see some limits into what we are actually receiving. So got one big here, some small ones there. One thing to keep in mind when playing with the sample rate is that we can not actually play it infinitely. There is a hard limit for one into the hardware itself. For instance, the USRP I'm using right now has a limit of 61, slightly above 61 megasamples per second. So the device is not able to sample at a higher speed than that. But even with really high-end systems like the latest USRPs 400 and something, that can go up to 400 megasamples per second, I believe. You usually or often cannot use all of them, and that's because you need a way to transfer all the samples into your device, into your laptop or your computer, to actually compute and do stuff on the samples. And so the main bottleneck becomes first the cable, the thing that communicates the sample to the computer. So either a USB cable in my case, or in the top end SDRs, you can get up to multiple 10 gigabit Ethernet cables just to feed that many samples and that many gigabytes per second of throughput. And for instance, the USB cable I'm using right now limits me in theory at about 15 megasamples per second continuously. It's not really able to feed that much more throughput reliably. And there is also the fact that, especially if you want to actually do something with the samples you receive, for instance, reception, you want to decode, then you need actually a good computation power on the computer that receives the signals, and sometimes it's not enough. The computer may become overloaded. And when it becomes the case, if I show you maybe at an extreme system, maybe if I go up to 50 megasamples per second, there we are way above what the throughput limit of the USB cable I'm using right now. And we get O's in the console. And this means overruns. So basically the internal buffer in the radio itself get filled up because they cannot empty fast enough through the USB cable. And so some samples get dropped. And that's the error you get. So it's quite bad when you want to actually receive all the samples and decode every bit and everything. But in this case, since we just want to look at like the shape of the spectrum and try to understand what's going on, and we are not really interested and we are not really able to go deep into the protocol levels and everything, it's not really a big issue just to look at the spectrum. So we can actually handle this situation. It's not really bad. And it also allows us, like in this case, to look at pretty much half the bandwidth of the ASM 2.4 gigahertz band, which is great. And here we can see that there is actually quite a lot of traffic here. We can see fairly wide transmissions, about 30 megahertz wide, 25, which is basically Wi-Fi signals, Wi-Fi packets. We can see fairly small ones, which are probably Bluetooth packets, and probably a lot of other things in the background. And so now at least I hope you've got some tools and some ideas to how to look at the spectrum. Okay, so now if I power up the microwave, we can start to see something a bit different from the background of Bluetooth and Wi-Fi signals. We can see big blobs of transmission, of interference, and these are what's leaking out from the oven itself. And we can also see that it seems to be quite wide bands, even though I was suggesting that it should be a narrow band interference, but here it spans basically the whole 50 megahertz or even 60 megahertz in this case of bandwidth. So what's going on here? If we look at the time domain display, we can see that the burst we receive from the microwave gets between -1 and 1. And that's actually quite bad because the radio system itself is not able to output above 1 and below -1. So basically it clips whatever sample that should go above or below that. And this clipping causes a lot of distortions. And this is the distortion that creates this wideband system. And so if we go back to the waterfall plot, but that we reduce the reception gain by quite a lot in this case, we can get a better view of what's actually transmitted. Here, we can see that it's actually way more narrow. The transmission is way more narrow, but it goes all over the place. It changes filter frequency, but every time it's quite narrow. And there was also one thing that quite interesting that you can notice from that is that this microwave seems to be doing some kind of pulse width modulation. So basically, when you reduce the power level you asked of it, it doesn't change the transmission power itself, but it just transmits it a bit less often. One thing to note here is that this type of pulse width modulation transmission scheme for the microwave itself doesn't seem to be completely frequent, doesn't seem to be what all microwaves do, and not all the time. And sometimes we can get something a bit simpler to read, such as this one, which I've taken a bit earlier, where we've got a transmission that spans a bit longer, and we can really see the narrow transmission scheme is basically a sinusoid that moves around in the band. And that's why it's a really good example of a narrowband interference scheme, because in the ISM 2.4 GHz, you always have the risk of getting this type of sinusoid pulse interference. Now that we've seen a good example of real-life interference, narrowband interference, we'll try to replicate that with a more controllable interference scheme. So I've made a very simple, again, flow graph that just has a noise source that I can filter that to reduce a bit the bandwidth, and I transmit that into another, the software-defined radio, and I allow myself to change the center frequency and the bandwidth. And so if I run that along with the previous system to actually monitor what's going on, and that maybe I go up to 20 megahertz and I look at the waterfall. We can see here this actual interference. It's this one. So it's fairly narrow and it's fairly powerful because the two antennas are quite close to each other, but it's really the same thing. And so we are going to use this interfering system to mess with two different types of transmission chains. So I'm going to close this one. As a comparison, I've got a small single carrier transmission system, so I'm not going into too much detail into what's going on inside. But basically, we are transmitting a QPSK constellation using a root phase cosine filter over the air. And at the reception, we use the matching cosine filter with some synchronization and equalization to help with the recovery. And we will plot basically the constellation. So as a baseline comparison, we have a fairly simple single carrier transmission scheme. I'm not going to go into too much details there, but we have a QPSK modulation that we use here that we pass into a root phase cosine filter and before transmitting. And then we have the same USRP, actually, just a different antenna. So it goes in, it goes out directly, but over the air. And we use that with a matching cosine filter, and then we've got some synchronization blocks to help us with the recovery of the signal. And so if you launch that, so here we have our single carrier QPSK transmission chain. And the most interesting elements to look for are the waterfall display on one side, where we've got in the middle our base transmission. And at the bottom, we've got different constellations, which are basically at different steps of the reception and the decoding. In blue, it's just with the time synchronization. In red is with the amplitude equalization, and in green it's at the end with the frequency and phase correction. So the green one is the main one to look for. I'm going to actually remove the other ones. And so when we approach our interference, we can see it's there, for instance, right now. I'm going to continue using the slider. But when we have the transmission, the interference over our system, our transmission channel, we get quite a lot of extra noise, which is to be expected since we have a noisy interference here. And this noise is basically here whatever the position of the interference inside of the whole block of data. But once we remove that and we put it outside, we can see that the noise is actually quite a bit reduced. So basically, when you've got one narrow interference somewhere in a single carrier transmission system, you get more noise in all the bits in the constellation equally. And now, if we change that into an OFDM transmissions system, so here I'm not going to go into all the details of all the blocks because it can be quite a bit complex, but this is actually the base, the default stock OFDM implementation of GNU Radio. So all the blocks are in the standard library. So, and this system actually implements packet-based transmission with a protocol and packet numbers and everything, and with synchronization at the reception and packet decoding, equalization, and quite a lot of things actually. So here I've got a quite similar display as just before, with at the top a waterfall display where we can see actually the whole width of all the subcarriers of our transmission chain. We can even see the different subcarriers, separate them individually. So we've got one block of 5 here, one pilot symbol here, one big block there, another pilot symbol, etc., etc. And on the left, we have our interference, which is actually right now not on top of our transmission, so it's not really interfering right now. From time to time, we can also see what is probably some Bluetooth packets, I guess. Some actual interference from the real world. And at the bottom, we have the combination of all the received symbols into one unique constellation plot. But we can also look at the subcarriers individually. So I've grouped them geographically, as one could say. So here I have the 5 of the left side block, and then here I have the middle block, etc., etc. It's a bit of a mess, but we can see here that basically all the subcarriers behave the same right now. But when I start to put the interference system on top of just, in this case, just the first subcarrier, we can see that actually only that first subcarrier is really affected. Maybe the second one also, because it's really neighboring and the filtering is not really steep. But we can see that basically all the other ones that are a bit further away are completely unaffected. Which means that in this case, we are going to have a lot of bit error for maybe the first 2 subcarriers, but here all the other subcarriers are completely fine, which is quite different from the previous situation where we had only one subcarrier basically, and so there was no real redundancy and no way to separate between elements of the system, of the channel that don't really work well, that don't really have a good signal-to-noise ratio, and the other ones that do work well. And so in this case, we can actually have transmission that's quite a bit more robust to this interference. And it's actually very probably one of the elements that made the standardization choose OFDM inside of Wi-Fi and Bluetooth, because in this ISM 2.4 GHz band, there is, as we saw just before, there is the large interference source of the microwave ovens that are present in basically every house. And so they needed a way to have their protocol at least somewhat robust, more robust to this kind of narrowband interference than the single carrier transmission could ever allow. If we play a bit more, we can also maybe change the center frequency. And then we can see that if we sweep that, we can really change which of the subcarriers is really affected. There is, though, one element that maybe you are noticing right now, is that sometimes the frame rates get slower here, especially if we compare that with the situations where there was no interference. And that's mostly because this transmission is packet-based. And so at the beginning of each transmission, there is a synchronization symbol. And this spans all the subcarriers. And so when there is one interference at one point, it may reduce the capability of the system to detect the synchronization system, and so some packets may be dropped. And so we get less received symbols, and so the frame rate, the amount of things to show here decreases. And that's something that is actually a bit complicated to handle. That's one aspect where OFDM packets may not be completely resilient to interference.